Hi everyone, I'm Safideh Mojalal and I'm a PhD student in Electrical and Computer Engineering ECE department. Today, I'll be talking about crucial issues in modern transportation, which is cybersecurity in transportation systems. Imagine you're driving a Tesla. The car sensors are constantly collecting data. They record your surroundings, they track your location, they even capture the audio from inside the cabin. Now, what if these sensitive information aren't secure? What if it's shared without your knowledge, without your permission? How would you feel knowing that your personal data could be accessed by third parties? This isn't just hypothetical situation. It's reality. In 2020, a data breach exposed the personal information of 7 million US drivers. In 2021, lawmakers raised concern about Chinese companies who were collecting data from self-driving cars during test drives in the United States. In 2019, ethical hackers showed that they can hack Tesla Model S. They could get access, they could control steerings, brakes, and other key functions. Again, imagine you're driving in a highway and suddenly an obstacle appears in front of you. As a human, you instinctively hit the brake immediately. But what about autonomous vehicles? Autonomous vehicles rely on cameras, sensors, and AI to detect obstacles. There is a processing delay between the time that autonomous vehicles detect these obstacles to the time that they actually decide to apply the brake. This delay known as reaction time. This reaction time is really important. Even a fraction of a second can make a difference in avoiding an accident. In my research, I'm working on a machine learning model that helps reducing this reaction time. It can help self-driving cars to respond faster and more accurately. Of course, accuracy is really important. Like, without accuracy, the system cannot be reliable. All right, let's see, why is cybersecurity so important? Cybersecurity in transportation isn't just about protecting self-driving cars from hackers. It can be about passenger protecting passenger data. It can be about protecting traffic lights and protecting management system. Like, what if hackers manipulate the whole management system? Or what if they hack public transportation networks? It can be about trains, buses, and metro systems. So we can say that cybersecurity is not all about all um, in protecting self-driving cars from hackers. It can be about other stuff like passenger data and security of public transportation. Um, let's talk about research methodology of my research actually. The core idea behind my research is inspired by a method that introduced by Google researchers in 2017. Before 2017, hospitals used to share their patient data with third parties for medical research. But Google's new approach helped hospitals to process their data locally without sharing the data with third parties. Let's call previous old approach centralized and new approach decentralized. I use a similar decentralized approach in my research to enhance data security in self-driving cars. Um, I'm trying to show that instead of sending raw data to a central server for processing, we can use a distributed model or decentralized model so vehicles can process their data locally instead of sharing their data and passengers information with central cloud or other vehicles. To show that to apply this, we need to define digital twin. A digital twin is a virtual model of a real world system, or let's say um, a virtual model of physical system. It allows us to test and refine our proposed approach in real world implementation. Now let's look at this picture. The left side shows centralized model, which is kind of old approach. Let's assume that we have three vehicles driving in a same location. I mean, same section of a highway. These in old approach, in centralized approach, these vehicles they share their data with a centralized cloud or central server. And that central server, which I have shown with a with a brain, pink brain, that brain actually processes the data, and send it back to these vehicles. Then they can um, they can predict the acceleration or trajectory, future trajectory. But on the right side, decentralized model propose an approach that actually works locally. Each vehicle has its own brain. They process their data individually instead of sharing the data with central cloud. As you see, my research shows that using an AI-based approach not only enhances data accuracy, not only helps for data security, um, but also it improves the reaction time. With local data processing, vehicles can decide faster. Vehicle can apply brakes when when they detect an obstacle. In next slide, I'm showing the acceleration prediction error. I'm using the error as a metric to show that centralized model actually works better and more accurate than decentralized model. All right. And this research that I presented, it is ongoing research. I'm still working on this research, and the future steps, I'm planning to apply another data set, Heidi data set. Heidi is a data set from Köln, a city in Germany. I'm also trying to apply alternative models, federated averaging, federated dynamic, LSTM, and IDM And as a next step, I would evaluate model robustness. And finally, I would compare the results of these four models. And um, I would like to thank my team, my research team, my clinic students, and all my committee members.